Greetings everyone. Today we're going to be talking about torque. So we can imagine that we have a bolt here that's fixed into, into place, and we just can't get this undone. So we can grab a hold with our hand and we want to get this screw out of there. So we're going to want to rotate it in this counterclockwise direction. You can't do it by hand, so what you do is you go grab a wrench, right? And this wrench is a very long handle here. And then in order to turn it counterclockwise, what we do is we apply some force in this direction. Grab it with your hand, you start pulling around like this. So there's a couple of things I'd like to point out right away. First is that what we have done is applied a force at some distance away. So that's this yellow line right here. And this yellow is the radius of our moment arm. So this, you might hear it called the moment arm. And basically the bigger the moment arm that you have, the easier it is to turn something. And we're going to apply some mathematics to this to clear up the relationship between all of these. And here we have a force that we're applying. Here we have two vectors, and the relationship between these two gives us our torque. So this torque is going to be related in some way to these two vectors here. So here's another schematic of our bolt looking on like this. Here we have our radius, here we have the force. So if you apply a bigger force, you're going to get a bigger torque. If you apply a longer moment arm, so you apply that same force from farther away, then it's going to be easier to torque it too. So that gives you a greater torque. So somehow these two are going to be multiplied together, in a similar way like we did our work was F dot X. Except here, the relationship between these two vectors is a little different. For work, when things were in the same direction, so this was X, maybe this is F, then you got a big work. When the force was applied normal to this X, you got nothing. So here was like Fx cosine theta. So when the angle is small, you get something big. When theta is 90 degrees, you're going to get no work at all. For torque, let's look at this case again. So if the force is applied at an angle 90 degrees, that doesn't show up, at an angle 90 degrees, we get a lot of torque. But what if you applied this force, let's just say, this way? Is that going to help you turn the screw? Or like in this case, maybe we apply the force like this, right? On our wrench. It's not going to work out so well. You're going to get a lot more torque if you apply the force perpendicular. So the relationship between these two is not a dot product. It's actually going to be a cross product. And we'll talk more about what this relationship is. Another way that a cross product is different than a dot product is that your result is also a vector. So this torque is a vector too, whereas the work, when this dot product, this work is just a scalar, it's just energy. Whereas torque is a vector here. So our relationship here is that this torque is related to R cross F. And we can talk about, just real simple, the magnitude of the torque is going to be R F sine theta. And that's how this differs from the, just to give you a reference, with the dot product, you had Fx cosine theta. So this sine theta, cosine theta, it's very important to remember the difference between these. With the cross product, you get a sine. So that means when you're 90 degrees, you're going to get the most out of this. The other thing is that the farther away you are, the bigger the R, the more torque you get. So Fa is going to end up giving more torque than this Fb here. All right, so let's put this into practice. So here we're going to have two equal masses. We're going to place them on some well, let's say that this ruler is massless. All right, and so here's our ruler, and we're going to place one mass over here at 10 centimeters, put another mass over here at 80 centimeters. Where do we want to put the pivot? So the pivot is going to be somewhere here, and we're going to say that the pivot is at x. So this is going to be 0, this is going to be our origin. And then now we want some x away from that origin, and then that's where we're going to put our pivot. So where should this x be in order for this thing to be balanced? So one way that we could do this is by putting the center of mass right over the pivot. So you can find the x center of mass of this thing and then put that right over this pivot. Another way is by considering the torques on this system. So here we have one mg. So this mg is going to be x minus 10 centimeters away from this pivot. And the other center of mass is going to be 80 minus x. And this guy's also mg. So if we want this ruler to be balanced, what we want is the sum of our torques to be 0. And torque is this Greek letter tau. So we want the sum of these torques to be 0. And we see that torque is actually a vector, so it's going to have some direction associated with it. So like forces, we had to say which way was plus and which way was minus. And here we're going to say that what's going to cause this thing to go clockwise, we're going to say that that guy is plus. And anything that wants to make this thing go counterclockwise, we'll call that guy minus. So here we have 1r, so torque is RF sine theta. And here both of our thetas are 90 degrees, so sine of 90 is 1, so we're going to just ignore that part right now. And then our r's are going to be this 80 minus x, then times the force, which is mg. And then now this guy is trying to rotate counterclockwise, so he's a minus. And then x minus 10, and then mg. And then we want that to be equal to 0. So if we want this torque to be in Newton meters, then we need to divide these both by 100. Divide this by 100. I now would like to cancel out a few of these terms. So one thing I would like to do is get rid of this 100. So I'm going to multiply both sides by 100. And I'm also going to divide both sides by mg. So that's going to give me 80 minus x minus 10 equals 0. So here we're going to get 80 plus 10, so minus minus. And then now both these x's are minus, so I'm going to bring those over to the other side. So 2x. So then x is equal to 90 over 2, or 45 centimeters. So if we put the pivot right at 45, this thing's going to balance. If you work this out with the center of mass way, you'd figure out that you just want the same distance here as the same distance here, and so you just want to put it right in the middle. This will be a little different if these masses are not the same, and that would also affect this relationship with torque. But this is why the center of mass things work. It's because the sum of the torques equals 0 if the center of mass is right over this pivot. So let's talk in a little bit more detail about this vector cross product. For the cross product, we're going to have tau is r cross f. So I said that this tau is a vector and that the magnitude of the vector is RF sine theta. So if we have two forces, A and B, that we apply at some R, which of these two is going to give us a bigger torque? If you said that A gives you a bigger torque, you'd be right, because the angle between the two is this 90 degrees. For B, you're going to get something smaller because the angle between these two is now much smaller. So this is theta. So theta is less than 90, so you're going to get something less than 1 for sine theta. The next part that you notice here is that this tau is actually a vector. So we need to know which direction is this torque. And this is a little bit funny. So this cross product is actually perpendicular to the plane that R and F are in. So right now R and F are both in the plane of your screen. So then this tau is going to be into or out of your screen. So these are our two vector directions for into and out of. So this is into and this is out of. Basically out of the screen that you're looking at right now, or into the screen. The way that you can remember these two is that if you had an arrow and it was coming at you or out of the screen, it would look like this. If you had an arrow and it's going into the screen, what you'd see is the tail feathers right here. So if we had a force applied in this direction, in this way, so here is our R, the moment arm, and here's F. Our torque is going to be R cross F. So what we do when we work out the direction of this is that here we stick our hand, and that this is going to be our fingers, and then this is going to be our palm, and then this will be our thumb. So I'm going to try to draw this out, and it's going to look pretty silly, but bear with me. So, and all this, remember, is with your right hand. If you use your left hand, you're going to get the opposite answer. So we call this right hand rule, or RHR. So here I'm going to stick my right hand in the direction of R. So what I need to do is I'm going to start with R, and R is pointing up, so I want my four fingers to be pointing up, and now my thumb is pointing this way just because that's easiest for me right now. And then now what I need is for my palm, I don't know, I have lots of fingers. So I want my palm to be facing in the direction of F. So what I have to do, so if this is my arm, right? What I have to do is I have to rotate my arm so that my palm is facing this way and my fingers, right, are facing up in the direction of R. So if my fingers are going this way, my palm is facing this way, my hand is pointing straight up right now, my palm is pointing to in this direction. My thumb is into the screen. So we could try that one more time with this example right here. So what we'd like to do now is say, what if we have R going this way, and now we have F going up? So for this, I'm going to stick my fingers in this direction, right? And here's my hand, and my palm right now is sticking this way. And now I need to rotate it so that my palm points up. So here's my fingers, and now my palm is pointing this way. So my thumb is pointing out of the screen. So go ahead, and if this confuses you, go again and try out and see if you can get your thumb to be pointing out of the screen for this case, with your fingers pointing in this direction and your palm is facing towards the ceiling. And your thumb should be pointing out of the screen. And then try this one again and see if your thumb will point into the screen. We'll do more practice on this in class. Let's work out another problem. So for this, we have a person who needs to change a tire. So there's a bolt here, and then there's a 70 kilogram person on a 60 centimeter tire iron. A force is applied 50 centimeters away from the bolt. But the tire iron is making a 30-degree angle with the horizontal. So here's our horizontal. The tire iron comes up like this. So here's our R. And now the force is directed straight down. Gravity determines that. So here's our mg, right? This mg is equal to this force. And so this theta is our 30-degree angle. So what we want is the angle between these two forces. So this angle that we're giving is not actually the theta that we care about. So for our torque equals RF sine theta, this theta is actually this angle up here. So if this is 30, this is 90 degrees, then this angle up here has to be 60. So our tau should actually be 60 centimeters, or 0.6 meters, and then times the force, which is gravity, so that's 70 kilograms times our 9.8 meters per second squared. And then now times sine of 60 degrees, because the angle between R and mg is 60 degrees. And what we're going to end up with is our tau is going to be 297. Then the units of torque are Newton meters, because here we have meters, here we have newtons. And then now you could say, well, which direction is this force in? So now we're going to stick our fingers in the direction of R. So my hand's kind of pointing up and to the right. And now I want my palm to be facing downward. So now my thumb ends up into the screen. So the torque is into the screen. For our last example, we have another Blu-ray player. And this Blu-ray player exerts a torque on a disc. So we've talked about what torque is. This is RF sine theta, the magnitude of it. Well, I'd like to draw you back to an analogy with linear mechanics, where force is equal to mass times acceleration. So torque makes something want to spin. And if something wants to spin, and you keep on adding torque to something, it's going to spin faster and faster. So what torque is doing is it's providing an angular acceleration. And that depends on the inertia of the thing that you're providing the torque to. So in our analogy back to linear mechanics, right? Force is kind of like a torque. Mass is kind of like this moment rotational inertia. Acceleration is kind of like this angular acceleration. So our torque is equal to the moment of inertia times the angular acceleration. So if we want to find the torque, we need to think about what is the inertia of the disc. And so Blu-ray, we're just going to say it's a cylinder, just to make things easy. And so that's 1/2 mr squared. So we can plug in R, which is this, we can plug in M, and then find our moment of inertia of this Blu-ray disc. Now we need to find alpha. The way that we can find alpha is, well, we can think about how the angular velocity changes. So here, omega final is going to be this 850. So let's convert this 850 RPMs into radians per second. So we need to multiply by 2 pi, divide by 1 revolution. And then now we need to, per minute, so we got a minute on the top, and then now we need to divide by 60 seconds. So when we multiply this out, we're going to get our omega final is equal to 89 radians per second. So here we have 89 radians per second minus 0, and it does this in 2 seconds. So then our angular acceleration is 44.5 radians per second squared. So then our tau, our torque tau, is equal to the moment of inertia times alpha. And so this is equal to 1/2 times this squared, and then now times the angular acceleration that we found. And what you'll find out is that this is equal to 0.02 Newton meters.